Okay, instantaneous rate of change. So a quick example first. Find the gradient joining these 2 points. So there's the first point, there's the second point. If we use the formula, we get the answer 3. So the gradient between these 2 points is 3. We can also do it using the rise over the run, and we get the same answer, 3. So if you think about it, y2 minus y1 over x2 minus x1 just means the difference of the y values and the difference of the x values. So it's called the rate of change, and we call this calculus. Calculus is obviously a much bigger branch of mathematics than just rate of change, but rate of change is definitely a part of it. So let's have a look at this point. So if this is the graph y equals x squared, and we're looking at trying to find the gradient at the point 2 along, 4 up, and we've drawn a tangent. We've drawn a tangent, we've worked out the rise over the run, and we've got a gradient of 4. So the gradient of the curve at the point 2, 4 is 4. But it's very difficult to draw tangents accurately. Now, if I was to randomly choose 10 of you and get you to draw that tangent, you'd all draw it slightly differently. And it wouldn't make a terrible amount of difference. It just might mean that somebody gets an answer of 4.1 or 4.2 or 3.7 or 3.9 or something like that. They'd all get an answer of roughly 4. But obviously, if you're building a bridge or a massive tower block, you want to be spot on, don't you? Okay. Now the gradient moves as we go along a curve. So if we look at x squared again, here, when x is minus 3, or the gradient, when x is minus 3, the gradient is minus 6. And as we move along the curve, the gradient changes. Now here's a special case, isn't it? Here the gradient is 0, because it's a horizontal line. M equals 2, m equals 4, m equals 6, and it'll change all the way around that curve. So it's going to freak you out a little bit now. So we're going to work out the gradient between A and P. And what I'm going to do is P is going to get closer and closer and closer and closer to A until eventually P and A are the same point. So this formula here, so differentiation from first principles, you're going to hate this. I hated this when I did this at school. Differentiation from first principles. This goes back hundreds of years. So basically, here's your little formula to work out the differentiation by first principles. But basically all it's saying is this is y2, this is y1, and this is x2 minus x1. So if you think about the h, here's the value, here's x2, here's x1, here's x2. So if we do this, take away that, we've got x plus h, take away x, we end up with h. So the h always is on the bottom. And this here is, so y2 is the value of the function at x plus h. And here is y1, the value of the function at x. Okay. And as we get closer, we can see that h is getting smaller. H is getting smaller. H is this distance here, yeah. H is getting smaller. H is getting smaller and smaller and smaller. And eventually, h becomes 0. Now, when h becomes 0, we've actually worked out the gradient at the point A. Here, we've worked out the gradient of the tangent between A and P. Here, we've worked out the gradient between A and P. So here, we've got an estimate. We're making a guess at what the gradient is at A. A better guess, a better guess, a better guess, a better guess. And here, we're not actually guessing, we're actually working out the gradient exactly at point A. And you won't be surprised to believe it, but the maths is a bit of a pain in the bum. So if we're going to work out from first principles what the differentiation of x squared is, this is the process we're going to use. Now, some of you might know the rules to use differentiation. So you might already know what it is, but we've got to use this process. So, because for this particular example, it's x squared. So we've got to have x plus h squared here, and here x squared. So this is the value x plus h, x plus h squared. For this particular example, it's x squared. Here, f of x is x squared. So we've got to multiply out that bracket. Don't forget, when we multiply out that bracket, we've got that middle term twice. So we have 2xh. Now you might be to see that the x squareds will cancel out. The x squareds will cancel out. Now the problem we have is when we make h 0, we're dividing by 0. And when we divide by 0 in mathematics, we cause ourselves a problem, don't we? So you might be to say here that we can take a h outside. We've got a h here and a h here. So we can actually take the h outside the bracket, cancel those h's, and we just left with 2x plus h. Now don't forget, we're going to let h become 0. So this is just the notation we use. We say f dash of x, so the differentiation of x, is the limit when h equals 0 of this function, of this collection of functions, of this expression. So if h equals 0, that will disappear, and we're just left with 2x. So those of you that knew the answer before we started, we've proved it. And you're going to have to prove it. You can't just say, oh, it's 2x. You have to prove it using first principles. Here's an even more horrible example. X cubed. So x plus h cubed. X cubed. Now we've got to do x plus h times x plus h times x plus h. So 3 brackets. That's what we get. Take care when you're doing that. The x cubes are going to cancel. We're then going to take a h outside the bracket, and we're going to cancel the h's. And then we're just going to let h equal to 0. If h equals to 0, all of that will be 0. All of that will be 0, and we're just left with 3x squared. If you know how to differentiate, you'd already know that that's the correct answer. So I would advise watching this video a number of occasions. So just some notation here. H is the difference in the x values, and the Greek letter delta means delta x, and it means the change in values of x. The top bit is written as the change in value in y. So this is the change in y values. This is your y2 minus y1. And because mathematicians are lazy, over the number of years, those Greek deltas have changed into d. So when we're working out differentiation, we often call it dy by dx, which basically means y2 minus y1, x2 minus x1. All right, let's have a look at an example. So I'll let you read that example. So basically what we're doing is a secant is just a line that joins 2 points. So we've got the formula x cubed plus 1. So here is x cubed plus 1 when x is 2.01. So 2.01 cubed plus 1. When x is 2, we've just worked that one out. 2 cubed is 8 plus 1 is 9. So that's our y2 minus y1. This is our x2 minus x1. x2 minus x1 gives us a value of 12.0601. Estimate the instantaneous rate of change. So the estimate 12.0601. Here's a really annoying example. So it's an exponential curve, and we're going to look at the secant, so the line that joins it at 3 and 3.1, so really close together. And here they're even really much closer together, so 3 and 3.001. If you probably were to draw them on a graph, you'd hardly notice the difference between the 2 points. So when x is 3, y is 8, because we've got 2 to the power of 3 is 8. When x is 3.1, y is 5.5742. Again, we just do 2 to the power of 3.1. Now what we're going to do is, so it's saying that the gradient is this. So what we've done is we've done y2 minus y1, x2 minus x1. So there's y2, there's y1, there's x2, there's x1, 5.742. There's the gradient. Now we're just going to do the same at these 2 points, at 3 and 3.001. So 3 to the power of 3.001 is that. So that's our y2 minus y1. That hasn't changed. X2 is just that value minus x1. So 5.547. So have we answered the question? We have answered the question. So 14 questions to do there. Again, as mentioned before, you might need to watch this video more than one time. Good luck.